to welcome Hans-Georg Feichtinger today from the University of Vienna. Well, he actually doesn't need an introduction, but I will still give one. So he's very, very well known in the field of applied harmonic analysis. He's one of the founders and also the head of the numerical harmonic analysis group, the NUHAG, at the University of Vienna, which he founded together with Stromer and Gröchenig. He's the editor-in-chief for the Journal of Fourier Analysis and its applications. He's known for work that has been very foundational in Gabor analysis. He's shaped co-orbit theory. He's introduced Feichtinger's algebra, known for that, modulation spaces, and Wiener amalgam spaces as well. He has also formulated the conjecture, which was then known as Feichtinger's conjecture, that was shown to be equivalent to the Cadison-Singer problem. So he's done really a lot of work, and he continues doing that in the field of harmonic analysis and applied harmonic analysis. So it's really my pleasure to have him here as an expert today to tell us more about the broad picture of Gabor analysis, state of the art in computational issues. Hans, without further ado, the stage is yours, let's say.
Thank you very much. It's a great pleasure to give this talk and also to kind of give you a wider perspective on the field, which at the time when I was a young person was considered by Jean Dieudonné an off-stream area, because who is doing abstract harmonic analysis is such a thing where everything is known. And if you look at Gabor analysis, virtually no theory existed in the mid-80s when I was already having all my qualifications, and where we started to get interested in these things. And actually it was this space, the Siegel algebra, which I called as zero, because it's a Siegel algebra in the spirit of Hans Reiter, and it has minimal property, therefore there's the zero. After a while, and in contact with the engineers, that's the group where Helmut Bölzkei came from, we realized that these function spaces, which are also the subject here, are quite useful, and the thing we're developing more and more, and now we have a very nice theory of Gabor analysis. I will explain what it is. And we are kind of coming back from the abstract theory to the applications, and what I will try to do is to give you a perspective and show you certain things, how to go from linear algebra to these theories. Now, the good thing, if you compare Gabor analysis, which is a particular type of signal expansion, if you compare it, let's say, with wavelet theory, is that you can do Gabor analysis on arbitrary, locally compact abelian groups. So I'm seeing myself in the tradition of Hans Reiter, who considered himself a student of André Weil. And so after doing Fourier series theory, Fourier transform, periodic Fourier transform, you can say, well, we can do it on any locally compact abelian group. So that's the common background. And if I go to the computational side, of course, we have the finite abelian groups. So everybody, I guess, knows what the discrete Fourier transform is. And the discrete Fourier transform implemented as the FFT, the fast Fourier transform, is one of the basic building blocks of Gabor analysis in the finite dimensional setting. So in wavelet theory, you don't have these discrete theories. You have to discretize the continuous. Whereas here we have the good chance that we can do everything, and we can do the finite theory in the spirit of linear algebra. And in this linear algebra spirit, we have the software around. And for example, I'm working with MATLAB all the time. And so we can do things without problems of convergence and so on. Now, if you go to continuous variables already on the torus, but that's not so much interesting for Gabor analysis, that's just Fourier series theory on the torus. But on the real line, you have infinite dimensional spaces. There's kind of no finite basis, so you have to work with functional analytic tools, and I try to separate these different aspects in my talk and also in the presentation. So why is it called Gabor theory? Well, Danish Gabor was suggesting that you can represent every function by taking the Gauss function the density of the normal distribution, shifting it in time by integers, multiplying with the pure frequencies, which are also periodic along the integer lattice. And in this way, you get a double indexed a set of building blocks. And he was hoping to get a unique representation of every function in this period. Now, Gauss functions obviously overlap. And for a long time, there was this false claim that because it's non-orthogonal, the expansion has to be difficult. I mean, it's like saying if you have a matrix which doesn't have a particular structure, like being an orthonormal matrix, it must be difficult to invert it. But we know, of course, that you have to look around, and if you find some structure, it might still help you to do this inversion. So that's one aspect. The other aspect is he was suggesting this integer lattice, the so-called Neumann lattice, and the commutation between the translation parameter and the frequency multiplication with the pure frequencies, because he thought that he wants to avoid that you don't have enough building blocks, and on the other hand, that you have too many building blocks and generate linear dependency. So I think in the modern terminology, he was hoping that you would get Array spaces. So every signal in L2 might have an expansion with uniquely determined coefficients. Now, it turns out that there are many obstacles to this. It's not just numerical instability or so. And also what we have learned over the years is that the concepts that you're actually usually still teaching in our functional analysis courses, which generalize the concept of generating system and linear independence, are not the appropriate ones. So we all say, well, when is an infinite set in a Hilbert space linear independent? Well, you're only looking at finite linear combinations, and if there is no trivial finite linear combination. But a normal person doing functional analysis should allow maybe at least absolutely convergent sums. And so that's exactly the difference here. In the Gabor setting, you have linear independence in the linear algebra sense, but not in the sense of sequence spaces. The same is true for generating. You don't want to have approximation, and if you want a better approximation, to change completely. So the expression of totalness, you would like to express every L2 function with as an norm convergent series, double series with the building blocks. And both properties are not true. That's the so-called Balian law principle. So the other aspect of Gabor analysis, quickly, is we should look at what we are doing with these Gabor expansions. So very often in the old days, they were saying the expansions would be very nice. They have a good interpretation, like a score. We have seen the continuous spectrogram before. And so we would see the information that is in the given signal. So we could analyze signals by looking at these coefficients. We can try to do a sparse approximation. We can manipulate it. Sometimes I'm showing the audio engineer's manipulations where he is changing the loudness of high and low frequencies in a different way over time. We have used it really very much, and that's where I learned a lot from Werner Kotzek from communication theory, to model slowly varying channels. Now, this is what is important nowadays for mobile communication. You can think of it as a moving average, but in this sense that you're having a convolution kernel, but while it's moving, it's not constant, but it's changing size a little bit. So it's like you have your multipath propagation, and then you go around the corner and you have a different multipath propagation. That's a little bit of different to the ordinary convolution operator. And to understand these systems or these operators, which really can be well approximated by Gabor multipliers, is one of the things where we have, well, just real world application. We even came up to patents which have not been pursued later then. Then you can discuss pseudo-differential operators, which for me are the natural setting for more general things than just differential operators with variable coefficients. So you are having effect where you are understanding better what's happening in the time frequency plane with the signals. And Schrödinger's equation, the applications of time frequency analysis to the Schrödinger equation, which I will not do here, have shown that this is really a very interesting perspective. Now, if we go to linear algebra and all the linear algebra I know I can also do in MATLAB, there are different qualities how we can use it. The first one is to do a demonstration. So at the beginning it was to say, well, I do something that I understand in the continuous setting, in an abstract theory, to show how it's in the finite dimensional setting. Then I realized that, well, actually, why should we go through abstract harmonic analysis in order to do these computations? Let's try to start with the linear algebra. So I will show you a little bit in this direction, but you can say linear algebra says we have a signal and we have a representation with a redundant system, and therefore you have many representations. Well, what is the best one? Well, the best one is the solution to the minimal normally square problem. So you have to introduce the pseudo inverse and or the more Penrose inverse, and all these things are done very nicely in general linear algebra terms, but also applied to Gabor analysis if you have like a toolbox which is able to do all this. And of course, we have such a toolbox. There's one kept by Peter Balázs, or the group of Peter Balázs at the Acoustic Research Institute, which is called LTFAT, the Large Time Frequency Analysis Toolbox. It has a lot of features which came from NUHAG, or I have my own one. But we can do really very many things. Now, sometimes we're not only using it to demonstrate things that we know already, but in order to find out what might be true. That was really very valid for Gabor multipliers. And it had a very interesting experience for me. I was doing these experiments, then I said, oh yes, I understand what's going on. I know how to translate the finite dimensional setting into the abstract setting of locally compact abelian groups. And I was writing a paper. And then my co-author, Krzysztof Nowak, was asking me, well, have you ever tried to see whether these conditions can be satisfied? And he was thinking of the continuous domain. And I said, yes, of course. Well, yes. All the examples, all the numerical examples look very much like it should be true. Well, of course, then I was sitting down and it was very easy to verify that you can satisfy these conditions in many cases or so. But it told me that I was already building my intuition completely on numerical experiments and that there is a possible gap. And now I'm really studying those places where maybe engineers have an intuitive understanding, but mathematical theory is not established, or where one should discuss much more in the spirit of like PD people, that the solutions to the discrete or discretized problem are really giving approximations with a guaranteed quality of the continuous problem. So this is really an area where a lot of things has to be done. So also quantitative aspects, I mean, you would say, you give me a Gabor system now with, I don't know, lattice constants which are irrational, and you would like to know the condition number of the involved operator because you want to invert it. But then I build up something which is very similar and which gives me numbers, and I would like to know, are these numbers reliable or not? And so I usually compare it with questions arising in numerical integration theory. So we have something, I mean, the status of the theory for me is comparable to the status of integration at the time of Riemann. We know that every continuous function has a Riemann integral, but you would like to have nice subclasses of functions where you know that efficient algorithms help you to gain a certain guaranteed approximation of whatever you have. Now, in the course of doing this Gabor analysis, we have developed a lot of algebraic structures, linear algebra structures, functional analytic structures, and function spaces. And while, of course, it's always tempting to make things more and more complicated, I found it important to try to find the minimal setting that still allows you to explain the most important things. So, and this minimal setting is really what I call the Banach-Gelfand triple. This is a mathematics colloquium, so I guess everybody knows the Gelfand triple consisting of the Schwartz space of rapidly decreasing function, the L2 space, Hilbert space, and the dual space of tempered distributions. So why should I bother to replace the Schwartz space? And my simple answer is, well, there are 3 arguments why I use it. First of all, of course, because I'm fond of these spaces and I found they're useful. But the point is, S0 is a Banach space. So as opposed to the Fréchet space with a countable family of seminorms, you can work with the ordinary Banach space, which has the big advantage that the dual space, which I meanwhile call the space of mild distributions, because it's a subspace of the tempered distributions, is the dual of a Banach space. So it's a norm space itself, but it's also endowed with the weak star topology. So we have 2 very important, very simple ways of convergence. Whereas people don't talk too much about convergence in the space of tempered distributions, of course, except the weak topology. So whenever you apply a sequence of functionals on a test function, you expect that you have convergence. So somehow the challenge was, which I've dealt with in the last 2 years, the side problem was, well, there is the well-known Lighthill approach to tempered distributions. So for people who don't like topological vector space, can you build a theory of tempered distributions just by taking sequences of good functions, and then you take equivalence classes, so by this standard completion process or so. And what I realized is, yes, you can explain that S0 prime is essentially a completion of S0 in this sense. And then you can show that L2 is contained in this completion or so. But if you look at the arguments, instead of using fancy topological space argument, what you need is more or less Banach-Steinhaus. So if somebody is giving you a sequence of test functions in your space S0, it's a Banach space, and you apply these test functions on other test functions, and that they're integrable, bounded, so there's no problem. And if all those things are convergent, then you know a sequence of convergent functional must be a bounded sequence, and then by Alaoglu you find it has to be a functional. If you give me a functional, of course you know how to regularize it. You convolve it, make it smooth, then you make it well decaying. So it's not so difficult to approximate a functional by such a thing. So it's very easy to also build a sequential approach to this theory of mild distributions, but that's just more or less a side remark or so. Now, again, just for an orientation, this theory requires a lot of things, and I think one can learn various terms from Gabor studying Gabor analysis. Well, I was very early introducing amalgam spaces. So actually S0 was introduced as a space which is locally like the Fourier algebra. So like a Fourier transform of L1 function glued together in a capital L1 and little L1 way. So absolutely convergent sum of pieces which are in the Fourier algebra. Okay, but that's a different topic. Now it's Fourier invariant. And so and this way I was coming to the modulation spaces. Modulation spaces are function spaces like Biezov spaces, where you replace the dyadic partition of unity, which is leading to Biezov spaces, by uniform partitions of unity. Also, this will not be mentioned, and underspread operators are the one that I learned from the engineers. That's not the topic today. What came also naturally was the theory of Banach frames for these spaces. Now, it has been mentioned that we have done Corbit spaces, so maybe I say a few words on this theory. I was already saying that if we go from linear algebra to Hilbert space theory, then the correct way of replacing a generating set is to say it's a frame. So I would say a frame, without giving you the inequality, the characteristic inequality, is a system of vectors that's like a basis in the following sense, or like a generating system, that up to some constant I know I can find coefficients that allow to represent everything, every element in the Hilbert space using square summable coefficients. Now, if you go to more general spaces and if you have a variety of spaces, and maybe you think now of a wavelet basis, and you think of the classical Bezout spaces, then you find out, oh, and that's what made them so useful. If I have a function in the Bezout space, then the corresponding coefficients are in a fancy mixed norm weighted LP-LQ space. Well, the same is true for those modulation spaces. You have Gabor expansions with the same kind of function spaces. The only problem that you have is I don't have any unconditional basis, or I mean I have, but not of Gabor type. And then you must be careful with whether you say every expansion has this property, or some expansion has the property, or the canonical property. But Banach frames are, for me, the natural setting of saying, well, you have function spaces of elements which are having some smoothness, like Sobolev spaces, L2 spaces, the space is 0 or so, and they have an expansion, and these expansions are in sequence spaces, and there's a natural correspondence between these two things. Now, if I try to use words only to say, well, what could you say in this setting? Well, then Gabor expansions, good Gabor expansions by definitions are those where the Gabor coefficients for L2 functions are L2 sequence spaces. Now, you can now guess what would be the corresponding sequence spaces which is surrounding little L2. And maybe you think of Fourier transform theory. There you have the square summable functions on the torus correspond to the sequence Fourier coefficients in L2. Well, think of Norbert Wiener. He said, well, I don't know, I want to avoid problems with pointwise convergence or so. Let's be on the safe side. Let's take the absolutely convergent Fourier series. Well, that's exactly the corresponding partner for little L1. People were then taking the dual space of this space. They call it the space of pseudo measures. And then people in distribution theory said, well, they have distributional Fourier transform and they are corresponding exactly to the L infinity space. So these Banach-Gelfand triple are exactly those triples of spaces. I will give the formal description later on, which correspond to a small Banach space, the dual space of this in the middle, a Hilbert space. And so for me, the classical theory of Fourier series, of absolutely convergent series, L2 and pseudo measures, going through to the classical Fourier transform into little L1, little L2, little L infinity is the prototype of a unitary Banach-Gelfand triple isomorphism. So even if you haven't heard this term, I think you will get the essence of this theory. Okay, so I'm not going further into these general things, so I will try to move now on with MATLAB and show you a few things. Maybe, I mean, of course, I will provide the slides. You can look up this. This is a series of papers where I tried to say, well, Gabor analysis has many aspects. If you look at the linear algebra aspect of non-unique representation or so, then you look at the second paper in this list. If you want to understand the Banach-Gelfand triple, you can take one of the master theses in Vienna or this paper with Elena Cordero and Franz Luev or so. If you want to go to the finite but general groups case, then this paper might be helpful where you don't have infinite series, but you can think of two-dimensional, multi-dimensional things to understand what you need. And if you implement this with function spaces, then you can, then the first paper with Franz Luev is a little bit going in this direction, then you can do all the things that you do algebraically on groups, also in the combined setting of elementary groups, for example. Okay, now I will try to move, and I hope everything works now, to my MATLAB. Afraid I have too many windows open. Here it is. Here. Okay, so I use now a MATLAB script, live script, and go through the material fairly quickly. So if I do a MATLAB, I choose a number which has several divisors, but also a fast FFT, and so that I can do all the matrices, I can invert matrices, and so meanwhile I should go for larger signal size, but 480 is a nice number. It's not the power of 2, but it has a lot of prime factors. That means the group, the cyclic group, has a lot of divisors, and very often I'm using now as a constant time shift by which I choose the translation 20. So I have 24 positions on the circle if you think of the torus. And frequency should be a little bit different. So in order to show certain effects, so I'm choosing 16. So 16 has 30 positions. So if you take those 24 positions in time and 30 in this, you see that I have altogether 720 building blocks for a 480-dimensional space. That means we're talking about linear algebra, and the redundancy factor, so the number of building blocks divided by the number of the dimension, is 3/2. I could show you a Mercedes star, which is the unit roots of order 3. That would be, in linear algebra terms, a frame of redundancy 3/2 for the two-dimensional plane. And somehow, if I would give you 2 scalar products with respect to this system, and the third would be missing, you would still be able to reconstruct. That's one of the good features of the frame theory, that you have some redundancy, but you can have some extra structure, and you have some robustness against erasure, for example. Now, the Gauss function that I'm using is something which is obtained by continuous Gauss function, normal density e to the minus pi x squared, by periodization, which is almost irrelevant here, and sampling. So if you would give me the number 144, I would sample a periodized version with length 12, so from -6 to +6 at the rate of 1/12. That has the effect that the FFT of the Gauss function in the discrete setting would be exactly the Gauss function itself due to the continuous invariance properties, of course up to the scaling, which is square root of n, to make the FFT unitary. So I have my routine that says, well, are 2 vectors equal? Maybe up to scaling, and the answer is yes, up to the factor 21.9, which is square root of 480. Now, another routine shows that if I show you in the discrete setting now a rotated, which is cyclic rotated version, slightly rotated, only 2 pixels, then its Fourier transform is multiplied with the frequency. Or if I do a time frequency shift, and the Rot mode means you give me a Gauss function, you rotate by 2, and then you multiply with a high frequency, and on purpose I was choosing 600. Well, that means I'm multiplying a full loop and then practically 120. So you see it is a frequency shift of 120. And the small time shift is the same that we had before. It's just this small frequency with 2 oscillations. Now, also in the discrete case, we can create B-splines. So they are convolution powers of the rectangular functions. The rectangular function is chosen so that it's a partition of unity, and so these are a discrete version of cubic splines. I'm just using this in order to create a partial sum, so I'm taking 3 of these elements from the partition of unity. I'm getting such a bump function. That's just on the one hand to show you the pupus, but then if I do it a 2-dimensional thing, so here I'm multiplying this plateau function, which is a tensor product of this bump function, with row number 4 and row number 7, for frequency 4 and frequency 7 of the 2-dimensional thing. So I'm creating a 2-dimensional function. Well, I didn't say Yeah, here you see. F is the Fourier matrix, so that's the matrix for the discrete Fourier transform. And of course, it starts with constant 1, and constant 1 is frequency 0. That's why I call the fifth row, or could be the fifth column, I call it F4. That's the frequency with full oscillations of your cosine or sine over the period of length 480. And frequency 7 is of course row number 8. I'm taking now a tensor product of these two, so I'm doing a complex valued function, a pure frequency, a plane wave. And of course, you see, if you look at the real part, it's something like a template like this. So one of the masterpieces in Gabor analysis on image processing was using a zebra as a template. Here is some other building image that I took more than 20 years ago when my son had this nice shirt. And when you do this, you can do the 2D Gabor coefficients. So you're decomposing more or less in building blocks of this type or so. And it's fairly easy actually to do thresholding. So I was just playing around a little bit here. Yeah. Here I was using a routine that is choosing it's discarding every coefficient which is smaller than 3% of the biggest value. So the thresholding was taken in terms of relative amplitude. The routine is giving me a filter which is just saying at which position in the 4-dimensional Gabor setting, or it's arranged actually 2-dimensional, should I put everything to 0 because the coefficients are so small. So it's really a signal dependent compression or so. And so I was just saying, well, how many surviving coefficients do I have? This is the number of ones in my filter. And I express everything in terms of percentage. That's why I have 100 times. And that's the number of elements. Now, here again, I was just using a very naive way of doing 2D Gabor analysis. You know, the FFT is obtained by doing row-wise and column-wise Fourier transform. So I could show you that the FFT2 command in MATLAB is realized by multiplying with the FFT from the left and from the right. You might ask yourself, well, is the order relevant? And the answer is yes, of course, because matrix multiplication is associative. If you do it first column-wise, it's matrix multiplication on the first term, and then from the right-hand side with the Fourier matrix or so. So you can guess what happens if you have a Gabor system and you take coefficients. You're multiplying now with a rectangular matrix, which is a format 480 times 720. So I really just compute this without taking care where these coefficients are. I'm taking a 700, getting all the coefficients in the 720 by 720 matrix. So this is the number of coefficients that I have here. So W1, W2 is 720 in my case. And I'm just doing this thresholding and do the reconstruction. And what you see here is that independent of the orientation and the roughness of the stripe, you see a very good representation of these local features, whereas of course fine details are discarded or so. I mean, I'm not saying that Gabor analysis is fine is a good tool for compression. You have to store the coefficients or so, but it's telling you a lot what the building blocks are doing. Another thing that you can get from discrete computations, or which we have seen, is what happens if we change the lattice constants. So if you do Gabor analysis, you can get the coefficients, maybe I should have explained this before, by taking the Gabor coefficients with respect to a dual window. I'm just showing you the dual window, and it's computed with some routine called GAB-DDD, and I'm changing the parameters here. You see, I'm taking 16, 16, 20, 16, 16, 20, or 20, 20. And I'm getting dual windows, which are all well concentrated in some way, but different in terms of shape. And so the more redundant situation, so that's the redundancy factor of 1.8. So it's still less than 2. gives you already a very nice, decent bump function. You can reduce the rate, and then you get either the dip or a side lobe, or you reduce it here. It's only 20% redundancy, but you get some dip and some side lobe. But the good thing is that you can reconstruct a function. Well, I was missing. Yeah, I'm not starting to play around now. No, here it's here. From the samples of a short-time Fourier transform. So yeah, okay, I should explain this picture. So what is the starting point of Gabor analysis? You're taking the continuous short-time Fourier transform in the discrete setting from a given random signal here. You're taking the at any shift parameter for your Gauss function, in this case, you're taking the Fourier transform in the vertical direction. So it's an FFT in that direction, and you shift by 1, 2, 3, and 480 pixels. And clearly, this is a highly redundant representation. If you look at this, actually, you look at the absolute value here because it's complex valued, and real imaginary part are highly oscillating or so. But then you get the impression that you should be able to recover it from the information only at these points. Now here I have marked a lattice, so it's a lattice in the periodic pattern, which also has 720 points. And the theory of Gabor analysis tells you we can reconstruct if we compute the corresponding dual window. And of course, you can also say, no, every point has some offset in the horizontal and the vertical direction. So take your family of Gabor functions, which has 720 building blocks. Each building block has so much time shift, so much frequency shift, and ask yourself whether you can compute coefficients or the minimal norm coefficients, which are producing the optimal representations. And then again, you would use the dual window. So what you have seen here is for the case of lattices, which are having, if you zoom in, such a pattern, very simple, horizontal, vertical, or the oblique is also possible. I don't go too much in the discussion here. So I think, yeah, maybe just this final comment. Here, what I'm doing here in MATLAB is the following. If you look at a general lattice, so this was the violet or the magenta points in my plot, then the Gabor family would be characterized by the elements in the point lambda, in the lattice lambda 1. Lambda 1 has 720 points. So these are these points marked here. Now, how would you organize them in MATLAB? Well, you would say this is a 0-1 matrix. And what are the positions? You go through the first column, the second column, and you count the numbers. So the counting would be number 1, which is 0, so to say. Then you go down by 16, so you have number 17. You have number 2 times b is 32, so it's 33 here, and so on. And then after a while, you're at the end, and then you jump, or you have a lot of numbers. And so this is the index set in the MATLAB spirit. And what I'm showing here is the following. I can take this continuous short-time Fourier transform and sample it. Or, and you have to know that I'm always using row vectors, or I take the collection of scalar products. Now, a scalar product of 2 row vectors is very easy. You take the first one as a row vector, and you take the second one. In MATLAB, the prime is conjugate and mark in the complex conjugate. So if you have x and y is the second guy, then I would turn it into conjugate of y1, and then of course the matrix product that I'm having here is really just the scalar product, x1 with y1 conjugate plus x2 with y1. So I'm just verifying that whether I'm doing the sampling and I want to reconstruct from the samples of the short-time Fourier transform, or whether I take this collection of scalar products, that's the same. And of course, the general theory tells us that we have to take the dual window and then use the synthesis with the dual window. Or you can ask me, well, can I build from the coefficients? Then I say, well, make another spectrogram, use the dual window to produce coefficients, and you're done. So this relationship is like a bi-orthogonality relationship, and that's of course very symmetric. And the bi-orthogonal of the bi-orthogonal is the original system again. Okay, now finally I'm trying to come to the slides with the Banach Gelfand triple, and I'm switching to a talk that I have given last year. In Palermo, I will see how much I can do here. I'm usually saying that if you're learning about Fourier analysis, and that was more or less my answer to students complaining that I'm using so many function spaces. I have many more such pictures or so, but I'm just telling you, well, people know the Schwartz space, which is the smallest of all these guys, and everything is happening inside the temper distributions. Of course, experts like to have ultra distributions, which have even smaller test spaces and even bigger dual spaces. I leave this out. Now, the only nice space in this setting, if you think of Fourier transform, is L2. We know the Fourier transform puts L2 into L2. Even the fractional Fourier transform has this property. Even if you don't know what it is, I would say think of it as rotation by an arbitrary angle. The circle is invariant. So what I try to tell you is there is this space as 0, and it's also fractional Fourier transform invariant, and the dual space is also. And everything that people are doing with LP spaces, amalgam spaces, unweighted modulation spaces, they're all sitting inside. So only look at this here. The blue object is L1. We know very well that the Fourier transform of an L1 function is the yellow object. It's not very easy to recognize. It's sitting inside the box, which is C0, so it's Riemann-Lebesgue for me. But C0 doesn't have a Fourier transform, so the inverse Fourier transform is a delicate object or so. And whereas you can read from this picture, S0 is very nice. It's a collection of functions which are Riemann integrable. The Fourier transform is in this space, they're Riemann integrable. The inversion theorem can be done with Riemann integrals, no problem. And if you're asking what is a pure frequency, then you find it inside this, or what is a Dirac delta, or what is a Dirac comp that is used. They're all inside S0. You don't need temper distributions. Actually, I don't want to deal with partial differential equations. That's kind of a private decision or so. You can modify the theory, of course, to incorporate this. But engineers usually want to do sampling, want to show that sampling goes to periodization, that the FFT is something for discrete periodic signals. And you really, I mean, you can say, well, these are finite vectors, but you can also say, no, these are really discrete periodic ongoing things. So a Dirac comp or a finite linear combination of Dirac comps is such a thing. It never ends. Does it have a Fourier transform? And the answer is yes, of course. You view it as an element of S0 prime. And if you know that S0 is Fourier invariant, again, I don't tell you the story why, but then you can say, well, the dual space also is Fourier invariant by a very simple rule. Sigma hat from this space applied to a test function f is sigma applied to f hat. You can say that's the restriction of the definition of a Fourier transform for temper distribution, but you don't have to know the surrounding area, you just have to know this. So what is the idea of the Banach Gelfand triple? Well, we make the world more simple by reducing this complicated diagram to a triple. And again, you can say, well, now this is an abstract situation. And I say, no, it's not more abstract than what we're doing at the beginning of any analysis course. We tell students, yes, you know how to compute the inverse of a rational number. The inverse of 3 over 4 is 4 over 3. But the real numbers are really much more nice. You can complete it. While I'm saying complete S0 with L2 scalar product, you get, of course, this isomorphic copy of L2. But if you take the dual space, you get something even larger. And with this triple, you have something which is really can be used like rational numbers sitting inside real numbers, sitting inside complex numbers. At the level of complex numbers, it's easy to explain why you have, let's say, addition theorems for cosine and sine, because you're saying, well, I can do exponential functions in the complex domain. And if I take real imaginary parts, I get something very obvious or so. So the same is true if you read papers on Fourier analysis, very often they have problems to stay inside L1 and well, in the big area, you can do everything. You can do classical Fourier series theory, you can do translation invariant of systems, you can do discrete Fourier transform, everything inside this, and you know suddenly that you would like to approximate one by the other. That's another important thing. Now this is, we can skip this here. Yeah, I have this story that but I don't do it here now. That I'm saying, well, what if you're taking 1 over pi, and 1 over pi is the number which is by definition the multiplicative inverse of pi. So you cannot prove this as its convention. Is it useless? No, because you know how to approximate a irrational number by rational number. So that's a game that we know. So if you transfer this idea to distribution theory, then you can suddenly understand that what engineers are doing by saying integral of minus infinity to plus infinity of e to the 2 pi ist is the Dirac delta. You would say, no, it's not Lebesgue integrable. I'm saying, no, what they mean is it's a symbolic thing. They mean integral over something multiplied with e to the pi dt is applying the inverse Fourier transform. And of course, also mathematicians agree that the inverse Fourier transform of constant 1 should be a delta, because the forward Fourier transform of a delta, Dirac delta, must be constant 1. We all know that convolving with Dirac delta is shift by 0, and shift by 0 is identity. So what is multiplication on the Fourier transform by something? It can be only multiplication by 1, which is this. So kind of this psychological aspect, which I only touch here a little bit, is that what I learned, or what we do in our daily life with rational approximation of irrational numbers and computation with complex numbers, if you take the same understanding into the world of engineers and physicists, I think you can, and interpret it in a distributional setting, I think you can do everything quite well. So in this sense, I have a kind of skeptical or new way of thinking of introducing this space. So the question was, how can I define this space for people who are not familiar with Lebesgue space and not L2? That's one way of several ways of introducing it, and many different characterizations. So for that talk, I was doing the following. We're starting with some reasonable, what I call it BUPU, uniform partition of identity or so. And then I'm saying, what is my space? Well, I'm multiplying this with pure frequencies, well, maybe like this. I define the short-time Fourier transform in this way. So I'm localizing with such a window, I'm multiplying with the frequency, and I'm doing this. And then I'm producing from a piece of music, as we have seen it at the introduction, such a spectrogram. Now I have to come up with the definition. Yeah, what is a mild Cauchy sequence? Yeah, how can I define the mild distributions from this setting? I can say, well, I would expect that if you give me a bounded continuous function and you're computing in this naive way a short-time Fourier transform, it will be a bounded function, and that's very easy. But then I'm saying, well, that's like the rational numbers. I want to complete it. So what is a mild Cauchy sequence? Well, a mild Cauchy sequence is a sequence of bounded functions such that if you take the sup, actually it should be sup over n of all these functions, the spectrogram is uniformly bounded. So you're saying that it's uniformly bounded. If you look at all these spectrograms of the involved functions hn, so sorry, it's a sup over n, and at every point it's a Cauchy sequence. So if you have this definition, it's clear that if you take such a mild Cauchy sequence, the spectrograms of the approximate or these members, they will have a limit, their spectrograms will have a limit. So all these mild Cauchy sequences at the end will have a spectrogram. And so roughly speaking, what I'm saying here, if of course you have to take in the same way as with rational numbers, I mean, yeah, to define real numbers, you have to make equivalence classes. So you say two such mild Cauchy sequences are equivalent if they have the same limit or so. And then it's you define now the spectrogram of such an equivalence class of mild sequence to be the limit of these joint things. The limit n goes to infinity. And in this way, you're producing the biggest space of all the objects which have a bounded spectrogram. Now, it turns out, and that requires some mathematics, but I mean, here I've not used much except the definition of a spectrogram and some manipulations in the context of Banach spaces or so. So it turns out that this is really giving you another equivalent definition of the dual of S0, which was introduced in many different ways, typically as a modulation space, which is you're taking all the L2 functions which have an integrable spectrogram. So you're doing this integrability condition now not on the Fourier coefficients, but on the short time Fourier transform. And then you're getting as a dual space all the temper distributions which have a bounded spectrogram. So you have again this transfer of information. And I was telling you, I mean, we have L1, L2, L infinity as a prototype. And it's nice that L1 is dense in L2. So it's also true here, S0 is dense in L2. But L2 or S0 are not dense in S0 prime in the norm sense. Well, that would mean that you have approximation of the spectrogram in the norm sense, which is the uniform sense. So if I would play the pure tone, you would see a horizontal line ongoing forever. If you approximate it with any test function, you would eventually have to drop down. So, well, how would you approximate constant one by functions which are concentrated? You would choose maybe partial sums of a partition of unity. So you would have longer and longer things. So that's exactly what we do. So usually I'm making the joke and saying, well, people in audio industry sell a CD and they claim that they give you a perfect representation of a piece of music. But in reality, they just give you 3 minutes and only from 0 to 20 kilohertz. But you have no interest in what happened before and after the piece of music. You're not a bat, you don't hear ultrasound. So this finite rectangular domain of 3 minutes in time and 0, or let's say minus 20 to plus 20 kilohertz, that's why it's 40, and that's why you have 44,100 samples. That's what you need to have a good representation, and that's the weak star convergence. So maybe that's, I would use this as a final statement. So if you look at the spectrograms, then you can explain that weak star convergence is, I'm just checking if I have anything else, yeah. Then weak star convergence is just pointwise or uniform convergence over compact sets. So better and better approximation of your spectrogram over larger and larger domains. So over longer pieces, maybe higher frequencies or so. So one way to define it, that's the non-canonical way, the absolutely convergent sums arising from the Gauss function, that's in one of the many characterizations with 0 is just the following. You're saying, well, if you have a Banach space, it should be a nice Banach space. It should contain the Gauss function. Well, it should be translation invariant in time and frequency. So you take all the time frequency shifted versions of the Gauss function and you take absolutely convergent sums. And that's one of the ways how you can characterize S0. So there are many other ways. As I said, the usual standard way in the book of Charlie Gröchenig is to say you take the short-term Fourier transform with respect to Gauss function or any Schwarz function that's always equivalent is integrable or so. But that is kind of quite intuitive. I must also say that's an interesting problem that we don't know. I mean, I don't know how to prove except for by indirect methods, how to use this definition to derive the properties of the space. So why is in this norm, the norm is of course the infimum over the coefficients, why is the translation continuous or so? That's not clear in this case. But with abstract methods, we can show that the space defined in one of the other methods can be also identified with this atomic characterization. And that's of course a reminding of Hardy spaces and so on. But I think I have used maybe more time than usual, and I should stop. I will stop the recording, and I'm open for questions. And of course, I have